So good afternoon. Welcome back from the break. My name is Matt Craig, and I'm happy to be one of the co-chairs for this session, where we're going to have a mix of machine learning and a discussion of open source community. It's my pleasure to introduce our first speaker, Anna Comesana. Did I get it? Okay. Who's a data science at LBL, and is going to be talking to us about using Python to accelerate sustainable aviation fuel R&D. So let's give her a warm welcome. It's her first in-person SciPy presentation, so.
Thank you. Thank you all for joining me today. The air is a little bit thinner up here on this platform, so just bear with me. I'm a little bit nervous right now. Now, oh no, did that happen? Wow, worst case scenario, okay. As some of you may know, one of the hardest fields to decarbonize is aviation, and that's because of very unique barriers and requirements, like different weight and size constraints. There's long innovation cycles, and there's of course a prioritization of safety, right? Like if batteries are too heavy, airplanes would fall out of the sky, and half of us would not be here right now, which just wouldn't be great. And so one of our best options is to look for alternative jet fuels. And today I'm really excited to talk to you about our efforts and the tool that we developed to help advance alternative jet fuel research and decarbonize aviation. First, I want to start by thanking my team, both at Berkeley Lab and at Oregon State University, as well as Oak Ridge National Lab for letting us use their computing resources. And I specifically want to acknowledge the Bioenergy Technologies Office for funding this research. And with that, let's start with a little bit of background on this project. The development of sustainable aviation fuels is severely limited by different social, technical, and regulatory barriers. For example, the property testing for a lot of bio-derived fuels is conducted pretty late in the R&D cycle, which sometimes leads to the scale-up of underperforming compounds, which really is just a lot of money and time lost. And so instead, machine learning can be used to predict the performance and properties of these compounds pretty early in the cycle and help de-risk this whole process. And that's what we set out to do with feedstock to function. Predict fuel properties to help identify viable fuel compounds. And to convince ourselves that we could do it, we started by predicting aviation properties of neat molecules. Now, in 2020, I presented and talked about our approach and the challenges we faced to predicting 5 key aviation properties that are necessary for the ASTM certification of fuels. And those were flash point, boiling point, melting point, yield setting index, and net heat of combustion. And since then, we've really refined and published our approach. And if you're interested in learning a little bit more about it, on both screens over there, I've put up the links to the paper that we published, as well as our tool, which is now online. But back then, we were using molecular descriptors to predict the properties of molecules. And molecular descriptors are things like number of carbons or eigenvalues of the distance matrix. They're just ways to mathematically represent the structure of a molecule. And one of the hardest parts of developing these models was just figuring out what molecular descriptors to use from an initial set of 5,000 to predict the properties of interest. And this is kind of what we ended up coming up with in terms of feature selection and model development pipeline. It's been simplified for the sake of fitting in a slide. But the key component here was really just the ranking of features to figure out which ones to use for each of our properties. And so for that, we used recursive feature elimination to rank the features by importance. And then we fit models by iteratively adding less and less important features. So for example, first we fit a model to only the top ranked features, and then features ranked 1 and 2, features ranked 1, 2, and 3, so on and so forth. And then we compare the performance of these models to kind of try to find an optimal feature set. And this ended up working pretty well. And we ended up with accurate models that really also were fairly interpretable and allowed us to look at the relationship between molecular structure and the properties that we were predicting. So that's kind of what we did for molecules. But as I mentioned, our end goal is really to predict properties of fuels and fuel blends. And those are a little bit more messy. They're a blend of molecules, right? And so that doesn't really lend itself to the calculation of these molecular descriptors. So to be able to come up with models to predict properties of fuels, we first needed to identify a viable set of features. And we ended up kind of settling on Fourier transform infrared spectra. And I'll talk more about Fourier transform infrared spectra in just a second, but it's essentially a method used by the refining industry to characterize the composition of a fuel. And then, like with the molecular descriptors, we needed to figure out what features to use for the prediction of each property, and then train models. And for that, we used some of what we learned from the molecular descriptors in our previous work, and developed a similar kind of end of pipeline and model training process. In a perfect world, I could kind of almost like stop the presentation here and say, this is what we did, and it worked great, and there were no problems. But that's obviously not how the world works. And so for the rest of this presentation, you'll be hearing a little bit more about the challenges that we face, as well as how we address them. Okay, so as I said, we used Fourier transform infrared spectra as features. And I'll be calling it FTIR Spectra from now on, because it's a little bit of a mouthful. So what is FTIR spectra? Well, it's a method used by the chemical characterization industry to look at the structure of a molecule, the composition of a mixture, as well as its quality. And the way this works is radiation passes through a sample, and specific wavelengths make certain bonds or functional groups in the sample vibrate. So then that radiation is either absorbed or transmitted. There's kind of two ways that you can collect this data. We collected absorbance. And this is kind of what an FTIR spectra looks like. And the location of the peaks tell us what functional groups and bonds are present in our sample. So for example, we see a little peak in like the 31 to 3,500 range, which is where the bonded oxygen-hydrogen group tends to vibrate. And so we know that that is present in ethanol. But we don't see a peak around 2100 where there's a specific aldehyde functional group that vibrates. And so we know that that's not present in here. FTIR spectra is unique to each molecule or blend of molecules. It's kind of like a fingerprint that gives us insights into the structure of your sample. And so this is what we ended up using to predict boiling point, flash point, melting point, density, and kinematic viscosity, which again are just properties that are necessary for the certification of new fuels. This came with its own fun new sets of challenges. The first one is that FTIR spectra is very much an art form, and it's really not used quantitatively as much. Historically, chemists are really just going to look at the approximate shape and use the approximate location of peaks to figure out, the composition of their sample. What they don't really take into account is that there can be a lot of variability in both the location of peaks as well as their magnitudes, just based on, whatever instrument or settings that you're using, or even just the environment in which you are taking your data. And so the first challenge was really just related to figuring out how to deal with some of this experimental error and noise that was just inherent to the data collection process. The second challenge was related to data availability. We decided to use liquid FTIR spectra instead of gas phase spectra, and that's because gas phase spectra is a lot harder to collect. For example, you need more of a sample. The problem there is that there's a lot of gas phase spectra out there in the wild, in published literature, but really not as much liquid phase spectra. And so we ended up having to collect a lot of this data ourselves, and we had to do so with 2 different instruments in 2 different locations. And so challenge number 2 was related to kind of harmonizing this data, since there's a lot of just inherent experimental error, to make sure that we just had a coalesced data set. And then the final challenge was, figuring out a feature selection pipeline to select useful features from an initial set of 15,000 spectra features, and then training our models. So let's talk a little bit more about the specifics of each of these challenges and how we address them. The first challenge, as I mentioned, was related to problems with the instrument itself. And an example of that can be seen through the baseline of the spectra. Each spectra have a baseline, which are the points that are supposed to be at 0, where there was no absorbance. And that baseline can be shifted up, it can be shifted down, it can be shifted by a slope. It really just kind of depends on the environment in which you're taking your data and truly just what the instrument decides to do. For example, the spectra at the top over there is the raw spectra that we took for pentene. And you can see that there's kind of like a bottom floor, a line that goes through that should have been at y=0, but has been shifted up. And there need to be better practices when collecting some of this data. But when we found that, the background wasn't collected, or it wasn't collected often enough, and we saw this kind of shift in the baseline, we had to get creative. And what we did was just ended up shifting the whole spectra uniformly by the mean of a region that was supposed to be at 0. And for us, that was kind of like that end region on the end, the 3600 to 4000. Because of our specific applicability domain to jet fuels and aviation, we knew that none of our samples would have any functional groups that would vibrate in that area. And so we knew that for all of our samples and future samples, that would have to be 0. So we just kind of took the mean of that area and then shifted the whole spectra up, down, whichever way it went. After that, we found that there were some negative values, which is physically impossible, right? You can't have negative absorbance. And so that was a bit of a problem. But thankfully, they were pretty small, and so we ended up kind of just clipping those negative values and making them 0. And then finally, we saw some noise that was just inherent to the instrument, and an example of that can be seen around the 1500 tick mark over there. There's just like a lot of peaks and dips, and if we zoomed in, it would just be like up and down and up and down and all over the place. And so to help with some of this, we just implemented a rolling window smoothing, which is really just, when you take a point, you take 5, 10, 15 points to the left, to the right, you average them, and then you move on to the next point. And the spectra at the bottom there that you see is the one pentene spectra after all of these transformations. And it looks a lot more like we would have expected, and it looks a lot more like a stereotypical spectra curve. But as I said, there's still a lot more experimental error kind of baked into the nature of this data. And so challenge number 2 was related to harmonizing data from different sources, since there's going to be inherent variability from instrument to instrument. For example, the 2 spectra in the top plot over there were collected with 2 different instruments with the same settings and the exact same sample. And they don't look the same. Now, chemists, again, are just going to look at the overall shape and the overall location of the peaks. And so those 2 spectra on the top look the same to a chemist, but we have to make sure that a machine learning algorithm also interprets them as the same. So how do we do that? What we did was essentially just implement some normalization. And what we did was divide the spectra by the sum of its values, essentially. So every new normalized spectra sums up to 1, and then the y-axis becomes a measure of what % of the curve is this peak height at. And this just kind of helps models get trained on spectral shape rather than the actual y values. And this ended up working pretty well. We see that the area around 3,000 and 3,500 gets brought closer together. Most importantly, we see that those taller peaks around the 1,000 area are a lot closer. And so now that we've more or less made sure that we have a coalesced database and that our 2 sources are a little bit more comparable, we can kind of get to developing models. But we had way too many features. And so the final challenge was trimming down some of those initial features with just some domain knowledge. Now, the spectra that we collected were in really, really small intervals. And this resulted in almost 15,000 spectra features. Thankfully, though, we can use what we know about both the instrument and the data collection process and our applicability domain and our samples to help trim some of these down manually first. For example, because of the properties of the crystal that we're using to collect our data, we know that the middle region around 2000 and 2500 is going to be mostly just noise. And this is just due to the crystal itself kind of interacting with the data collection process. And so we knew that we can kind of just drop some of that. The second example is that region at the end that I mentioned earlier, the 3600 to 4000. Again, like because of our applicability domain to jet fuels, we know that that's going to be 0 for any of our samples and any like future samples that we collect. And so we know that we can just get rid of that from the beginning. But even after dropping these two sets, we ended up with still a pretty imbalanced data set. And so to help with that further, we implemented two matrix decomposition methods. The first one is non-negative matrix factorization, or NMF. And what NMF does is decompose the original data matrix into the product of two smaller ones. And because of its non-negative constraint, it does so in a pretty intuitive, additive way. So the rows of H, or the basis matrix, are going to be basis elements, and we can kind of interpret them as the fundamental building blocks or patterns from which we can reconstruct our original data matrix. Then the columns of W are kind of the coordinates of each data point or each sample in the basis of H, i.e. how to reconstruct an approximation of that sample from a linear combination of those building blocks in the H matrix. And you can kind of think of it almost as the importance of each building block for each sample. So, you know, the first row, second column of that W matrix would be the importance of the second component in the first sample. This sounds great, we love it, but there's a couple of caveats here. The first one is that NMF doesn't guarantee single unique decomposition, but this can kind of be tackled with proper regularization in the objective function. The second problem, which is the bigger one, is that it's hard to know how to choose a factorization rank K, right? It's hard to know how many components to decompose your matrix into. But again, there's things that you can try, you know, like the trial and error. You can ask for insights from experts. You can look at different information criteria or singular value decomposition and looking at the decay of singular values. So there's kind of different ways that we can figure out how many components to decompose our matrix into. The second method that we tried, it was principal component analysis, or PCA, which I'm guessing a lot more people are familiar with. And what PCA does is just decompose the variables in a way that prioritizes information kept. And so the new variables, or principal components, are constructed as linear combinations of your initial features, and those principal components are uncorrelated, and then most of the information within your initial features is kind of squeezed into the first couple of components. So there's an inherent rank, and by information here I really just mean largest possible variance in your data set. So we used both of these methods separately for all of our properties. And then we used what we learned from our previous work with molecular descriptors to develop a similar kind of end of pipeline. So what we did was use recursive feature elimination to rank the components that we got from PCA and NMF separately, and then we fit preliminary models to bigger and bigger feature sets by adding components that were ranked as less important. So for example, first we only fit a model to the top NMF component, and then top 1 and 2 components, top 1, 2, 3, etc. And we look at the performance of each of these models to evaluate the relative accuracy of each feature set. And then we just kind of go with the best performing feature set, and we choose that. And we do model training with the help of TPOT. TPOT is a Python-based tool that automatically fits thousands of pipelines, including different model architectures and hyperparameters to your data, and then returns the optimal one. So it essentially just does a huge, huge grid search for you, and returns the best model that it found. And the models that were returned by TPOT are the ones that we are currently using. Before I talk about the results, a nifty thing about our approach, and specifically the use of NMF, because of its additive nature, is that we can really interpret what the model is deeming important or not in a pretty intuitive way and decide if it's valid. For example, these are the 3 components that we decomposed our viscosity matrix into, and we found that only using the 2 red components yielded best accuracy. And so we can then look at the bonds and functional groups that are present in that 3rd component that wasn't used and decide, is this something that could be related to viscosity? Is it fair that this is not included? For example, that little peak over there with the arrow represents monosubstituted alkenes and 1,2,4 trisubstituted alkenes. Now, I'm not really a chemist, but it could be that this group is not as much of a factor into the viscosity of a fuel or a mixture, or it could be that it's just not as much of a factor as other alkene groups, which are in the 2 red components. So we can kind of just use math and science to validate this model and corroborate its results. Now, speaking of results, we did this for all of our properties, but how did it actually do? And here we have some side-by-side parity plots. On the left is the current work with FTIR Spectra features, and on the right was the previous work with molecular descriptors. Now, we are getting better error metrics with the FTIR model, but that's kind of to be expected, right? Because we have a much, much smaller database that is also a lot less diverse. It only contains compounds and molecules that are related to jet fuels and aviation. But considering some of the challenges that we face with our data and some of the choices that were really just made empirically, this is a great start. I'm sure you all noticed, though, how sparse that parity plot on the left looks. And so that's really the biggest thing with our approach right now. It's promising, and it looks like it's working well, but much like Oliver Twist here, we just need more data. There's still a pretty big imbalance that we have between number of features and samples, and this could be causing some issues. For example, I mentioned that NMF doesn't guarantee single unique decomposition, and we are seeing some variability when we fit it multiple times. And this is something that could be due to just having so many features, truly. And cutting down on the number of features before NMF and PCA could also help make the model more interpretable and increase the chance of finding meaningful relationships between the composition of our samples and the properties that we're predicting. There's also some other things that we need to tweak and iron out. For example, the rolling window width by which we are smoothing, or our normalization method, right? I mentioned that our normalization method helps models get trained on spectral shape, but if the magnitude of those peaks is directly proportional to the concentration of a bond or a group, is this really the best way? And that's, at the end of the day, our primary goal is just to get more data so that we can answer some of these questions. And we do have spectra for some reference fuels that we recently got. And those fuels have easily calculated properties like boiling point. And so our next steps are really to just add these to our data and investigate our approach and either validate it or find the parts that we need to improve and like the knobs that we kind of need to turn and tweak. And so, yeah, with that, if y'all have any questions, I'll take them now.
Thanks very much. I would ask that if you have a question, please come on up to the front here. And we should have another microphone we can use for questions. It's on its way up here. So, as Benoit expressed it to me before the session, we're chairs, we don't have legs, we can't walk, so you have to come to us.
So is there a reason you chose not to use a gas-based FTIR protocol, other than the difficulty or the expense in getting like equipment?
That it was so. I don't know if everybody heard the question, but was there a reason that we chose not to use gas phase spectra? I think truly with a lot of our fuels, I mean, there's like with a lot of fuels, they're very volatile, especially like with gas phase, and so that really just the difficulty of taking that spectra is insane. And you also need a lot more of a sample, and so it would make the whole data collecting part of things a lot more expensive. And so that's kind of really why
Makes
we chose
sense. I
liquid.
wondered if you had an auto sampler or something similar, like an injection port auto sampler that would allow you to do that. It sounds like
No, we do not. Yeah.
Okay.
Hi, thanks for the presentation. That was super interesting. I was just curious, I think I maybe missed it. So when you're picking features using this, like these spectra, is it just like by wave number? Now I know you did some reductions, but do you bin by like some specific, like, I don't know, 1 wave number, 2 wave number, some range?
Sorry, could you repeat that?
Just like, what are the features that you get from the plot? Like, are you doing it just like absorption on a single wave number or some small
Yes.
interval? Yeah.
Yeah, on pretty small intervals, and I think the actual interval is like 0.25 or something, right? And the range goes from 650 to 4,000.
Okay.
Yeah, and so, yeah.
Great. No, that's cool, and I understand. Yeah, makes sense about removing the parts that don't show up in the spectra.
Yeah.
And then my other question is just on the output of eventual successful models will be some combination of wave numbers or absorption spectra bands, essentially to target. So when we're talking about experimentalists trying to do this, that's not something they can just like change composition of fuels, right? So like, just do you have any comments on like how someone use the outputs to come up with like kind of better fuels?
Oof. My background is not in chemistry, and so my answer to that question would be very, very limited. We can talk a little bit more about it later, I think, but I think I would want to look some things up before I answer that question so I don't get in trouble. Thank you.
Really fascinating work. So I'm curious about whether you feel the issue with the sparsity of your data right now is more of one of depth or breadth. I guess I'm asking, do you see a future of incorporating additional analytical upstreams to this? For instance, Raman spectroscopy, which measures different molecular dynamics. Would that make the model more effective if you could get that data, or would it just introduce confusion and it'd be better to get more FTIR spectra?
I think there's been some challenges that we've even just faced with, for example, transforming the like absorbance to transmittance data, which there's also a lot of like, and so I think given that and given so much of just truly the experimental error that we are seeing, and you know, a lot of these steps and a lot of these like challenges that we've had to address, we found because like truly we tried to fit a model and it was like, wow, well this is getting really confused. And why is it getting so confused? Oh, it's because there's so much error everywhere. And so I think that it's something that we would maybe just have to carefully look at before we really go any other route, if that makes sense. Not sure if that answered.
That does. I guess my second question then is who are the contributors of these spectra? How many different, I guess, groups are contributing spectra? And have you tried to align on one lab with like the throughput to collect these on a single instrument? Is that something that you've looked at?
Well, we have been collecting it with some of it at Berkeley Lab, some of it at OSU. We really just have somebody like manually do these things.
Okay, so there's not that many different
it's,
instruments involved.
yeah.
It's just the variation on the individual spectra. I gotcha.
Yeah.
So for other follow-up questions, I invite you to post them on Slack. And in the meantime, let's thank our speaker again.
Mm-hmm.